Welcome back to Applied Materials and Corrosion. We're back in the lab again. So today we've got a new situation. We've got copper electrode, which is plugged into one of our measurement ports. We're going to measure voltage. It's going to go into a copper nitrate solution, which will then have a copper 2 balance, and so it'll be like a rubbish reference electrode. We're going to use a salt bridge to a buffer solution, and the other electrode is made of iron. So now we're going to measure effectively an iron copper battery, but we're effectively also going to measure the same thing that we're going to see from our pour-by diagram. We're going to measure how different the voltage is in different situations. So now we've got it all set up, I think. I'm probably messing around in the background somewhere. I might speed it up to do that. So let's do that now. So here I am at high speed, gathering all the equipment and putting it all together. It's not as high speed as I thought it would be. Here it goes, buffer solution being used for the salt bridge. It's not a very good salt bridge, but never mind. We're going to apply the iron and the copper, clamp it all up. It works better in high speed. Connect up to voltage, and we will see a voltage between the two, which will eventually settle down. We've gone back to normal speed now. It'll eventually settle down at 600 millivolts somewhere. And here we have the same situation, just a little bit longer. So now the voltage is going up again. Just to make sure that the reference electrode is the same, this is done all in one run. So I'm going to take this out in a moment. So we've got 632 going up a little bit, so 640 maybe millivolts compared to the copper. It's negative, remember, in this case. So this is the way I've connected it this time, minus 630 millivolts, going from buffer pH 7 into buffer at pH 10. So flip out my bit of nasty towel, put it into buffer at pH 10. This is obviously not super clean, but the buffer will help a little bit, giving it a bit of a wipe so that I don't put too much pH 7 buffer into my pH 10 buffer, so that we get the same result. Now we're going to a completely different potential, 393 millivolts, and we can think about that in terms of our pour-by diagram. At pH 10, the oxide layer, the oxide hydroxide layer on our iron is way more stable than it is at pH 7 or pH 4. pH 7 is okay, but it's a different oxide. pH 4, it's completely open. So that was more stable, meaning there was less voltage compared to the stable copper 2 plus. Now we're going to go into a different situation, pH 4. So this is also a buffer solution. It's a standard buffer that I just used some straight out of the bottle. So I'm not quite sure what this is, probably citrate. I'm just poking it so that the salt bridge is not touching my copper electrode. The copper needs to be in the copper 2 plus solution to have a constant voltage, otherwise we will have a different constant voltage, so we can't compare it. So remember, we had 630 and we had 390, and this is going to go to a similar voltage as the pH 7. 630, it got there a lot quicker because it's completely open to corrosion. And we can think about why that might be the case looking at the pour-by diagram for iron. But for today, or for this particular video, that will do. We can see that there is a different equilibrium voltage. Effectively, it's a quasi-equilibrium because if we waited forever, all the iron would dissolve. But over time, we can see that there's a comparatively similar voltage at pH 4 and pH 7, and that is there's a much lower voltage apparently on an iron electrode at pH 10.